Hello, and welcome to the first video for Math 180, Calculus. Before we get started, I'd like to share some advice about how to learn efficiently and effectively in this class. First, if you feel that the videos are going too fast, then remember at any time you can pause the video or replay a part that you'd like to watch again. There's no shame in watching reruns. Second, if you feel that the videos are going too slow, then I encourage you to increase the playback speed to 1.5 or even 2 times the normal speed. And if you want to hear what I sound like when I just wake up, try changing the speed to 0.5. Just kidding. Finally, I highly encourage you to print out blank copies of the notes and fill them out as you watch the videos. This writing will enhance your memory of the concepts and make it easier to jot down key ideas that you want to remember. Sound good? Great. Now, if you had me for pre-calculus, you might remember that at the end we gave a brief trailer about the movie that we call calculus. For everyone's benefit, I'm going to do the same here to lead into our first topic. It all starts with a joke. A student in a math class asks, "What's infinity?" The math teacher replies, "Think of a number." The student says, "Okay, I've got one." And the teacher says, "Good, that's not it." So what exactly is calculus? Some summarize it by saying that it's the study of continuous change. For example, calculus can help you get from a distance function to a speed function by looking at the distance function's rate of change. Or it can help you get from the population function to the population growth function by looking at the population's rate of change. To get there, we need to understand more about infinities and infinitesimals. And as the joke implied, the first thing you should know about infinity is that it's not any particular number. It's more of a behavior that a sequence of numbers can have. For example, the sequence 1, 2, 3, 4, 5, etc. doesn't approach any one number. But we say it approaches infinity. What is an infinitesimal? An infinitesimal represents a behavior where the values are approaching 0. For example, the sequence 1, 1/10th, 100th, 1000th, etc. gets closer and closer and closer to 0. In fact, as close to 0 as we like. Generally speaking, the concept we want to understand that underpins all of calculus is the limit. When you first hear the word limit, you might think of things like speed limit, or the limits of the known universe, or supplies are limited, so buy now. But the mathematical concept of the word limit is a bit different and has a very specific definition, one that helps us grapple with infinities and infinitesimals. Much later in the course, we'll learn this formal mathematical definition of limit, but in this video we're going to focus on understanding limits visually. Let's head to the notes to get started. Hey, I'm up here in the corner. All right. So I think it's best to ease into this by first reviewing what it means to plug something into a function. So here for example 1, we've got this piecewise defined function. So it consists of these many different pieces. And we're asked to find or evaluate the function at these given x values. So find f of 0, which means plug x equals 0 into the function and figure out what the output is, what the y value is. So to help to get oriented again on the graph and understand what all of that means. Now, one of the ways to think about this visually, so first we'll focus on f of 0, is to, so here's a bigger version of the graph, is to think about when we plug a number into a function visually, our eyes first go from the origin over to the place on the x-axis that we're plugging in. So let's say that we're plugging 0. That's the first thing we're going to plug in. So I would take this red dot here, which represents the input, represents the x value that you're plugging in, and drag it over to an x value of 0. Then what happens is our eyes go up to the graph, and then over to the y-axis. Now, in this particular case, we're on the y-axis, and so we can see that the output here is going to be 1. So f of 0, we can say, is equal to 1. When you input 0, the output is 1. Let's go over here and write that down. This is equal to 1. So our next job is to find f of 1. So we'll take our input, we'll drag it over until it gets to an x value of 1. What do you think is going to happen? What is f of 1 going to be equal to? If you said 3, that would be correct. Here when we drag it over to 1, and here it locks right into that x value of 1. Notice that when we go over to this x value and then we look up to see where the graph of the function is, this open circle here represents not a point in the graph. So that just happens to be a point that part of a graph is connected to, but it's not actually a point in the graph. So then we continue through that hole up until we hit this filled in dot. The filled in dot represents that that's a part of the graph. So then our eyes then move over to the y-axis, so they go horizontally to the y-axis, and we can read off the y value of 3. So f of 1 is 3. F of 1 is equal to 3. Let's look at f of 2. What do you think f of 2 is going to equal? In this case, it's a little tricky. So here, if we drag the x value over to 2, and we look up and we look down, there is no graph of the function. All we see is an open circle down here, an open circle up here, but there's no filled in dot, or there's no piece of the graph to speak of. So in this particular case, f of 2 we can say is undefined. The graph of the function is undefined at 2. What about f of 4? Let's check out f of 4. What do you think f of 4 is going to be? If you said 2, that would be correct. So if we drag our red dot over to an x value of 4 along the x-axis, and we go up to the graph, we see the filled in dot is right here, and then go to the y-axis and we get an output of 2. So f of 4 is equal to 2. What about f of 5? What's that equal to? If you said -2, that would be correct. We look through this open circle down to where the filled in dot is, and then read off our y value, which is -2. What about f of 6? If you said 0, that would be correct. So here we drag the x value over to 6, and we happen to be sitting right on the graph of the function. So when we look over to the y-axis, we look at it, we read off a y value of 0. So f of 6 is equal to 0. And lastly, f of 7. What is that? If you said undefined, that would be correct. Here it's showing an output of question mark, but we're going to write undefined. If a function defines outputs for given inputs, this particular input has no defined output, no output that's associated with it. 7 does not have an output associated with it, so it's undefined. So f of 7 is undefined. Now, as we mentioned, the limit is a core concept in calculus. All the other important concepts in calculus, derivatives, integrals, even continuity, are defined in terms of limits. So to get an intuition about what a limit means, we're going to approach this again visually. Here, you want to think about an animation of inputs and outputs rather than just a set input corresponding to a set output. So you want to think or ask yourself, what is happening to the outputs as the inputs are changing? Or put another way, what is happening to the y values as the x values are changing? And in terms of notation, you might remember from pre-calculus that x with a right arrow and then a number with a little superscript above it with a little negative or positive. What this means is x approaches 1 from the left and then the x arrow 1 to the positive means x approaches 1 from the right. You can think of it like this. If you have a number line, this is the number line of x values, and if this is 1, then 1 plus a little bit, 1 minus a little bit is going to be over here on the left side. So that little negative superscript can help you remember that you're doing 1 minus a little bit. So that would help you remember that you're approaching from the left. So this is x approaching 1 from the left. And then if you have a little plus superscript or positive superscript, that means that you're 1 plus a little bit. So you're over here on the right side of 1. Still approaching 1, so you're still getting close to 1, but you're on the right side of 1. You don't want to be on the wrong side of 1. It's a pretty nasty number. All right. So that's a visual picture of where your eyes are going in this animation of x values. And then at the same time, you're going to be tracking an animation of y values, of outputs, and seeing where those y values are headed. So looking at what we're going to try to be answering, for example 2, we have the limit as x approaches 1 from the left of f of x. So this is saying what is happening to the y values. F of x represents the y values, right? Like up above we said f of 0 equals 1. The y value of f when x is 0 is 1. So f of x represents the y values of the function. And so we're asking what is happening to those y values when the x values approach 1 from the left. Let's go over to our graph to check this out. So I'm going to drag my x value dot closer and closer to 1 from the left. So here we're on the left side of 1, but we're going to get closer to 1 from this left side. So we're never going to cross 1. We're not going to be going like all the way this way. We're going to be getting closer and closer to 1, but staying on the left side of 1. And we're going to think about what happens to those y values. Where are those y values getting closer and closer to? So what do you think? If you said the y values are getting closer and closer to 2, that would be correct. As the x values get closer to 1 from the left, so here are the x values of like 0.91, 0.92, 0.93, 0.94, the outputs are getting closer and closer to 2. In fact, here, when you round, it actually gets exactly 2. But technically, these are getting closer and closer to 2 and never actually equal to 2. So what we would say is that the limit as x approaches 1 from the left of f of x, we're going to say equals 2, even though we never actually reach it. We just say that that's the place where the y values are headed when x approaches 1 from the left. So even though we never get a y value that's equal to 2, we're saying that the y values are getting closer and closer to. The limit as x approaches 1 from the left is 2. All right, well, let's check out what happens when x approaches 1 from the right. So we'll come over here, we'll drag our input dot, getting closer and closer to 1 from the right, and what would you say that the limit is in this case? The limit is 3, that's right. Because in this case, the y values are just 3, 3, 3, 3, 3. They're getting closer and closer to 3. They're actually sitting at 3 the whole time, as along your journey as x approaches 1 from the right. So for this limit, we're going to write 3. All right, let's check out to see what happens as x approaches 2 from the left and then 2 from the right. So dragging our input dot, we're going to approach 2 from the left, and what does it look like the limit as x approaches 2 from the left is of our function? That's right, it's 3. Because the y values are getting closer and closer to 3, even though we don't actually have a function value at 2 at all. There is no function value. F of 2 is undefined, and yet the limit as x approaches 2 from the left is 3. What about the limit as x approaches 2 from the right? If you said -1, that would be correct. See how the y values are getting closer and closer to a y value of -1. Again, they never quite reach -1, but they get closer and closer to -1. So we have 3 coming in from the left, -1 coming in from the right. We'll head over to 4. So what happens as x approaches 4 from the left? What are the y values doing? If you said getting closer and closer to 2, that would be correct. And then what about if the x values approach 4 from the right? What are the y values doing? That's right, they're getting closer and closer to 0. You can see that tip of the arrow getting closer and closer and closer to y values of 0, a y value of 0. Okay, so 2 for the left and 0 for the right. Look at 5. So as x approaches 5 from the left, what are the y values doing? Getting closer to -1. And then what about as x approaches 5 from the right? What are the y values doing? Again, approaching -1. So in this case, from each side, the y values are approaching -1. And this is despite the fact that f of 5 is equal to -2. So the limit and plugging in a specific function value are different concepts. The limit is more about the path along the curve. It's about the journey rather than what's happening at a particular x value. So you want to be thinking about, with limits, you want to be thinking about traveling along these curves rather than plugging in a specific value. More of an animation, as we said. So then 6, let's see what's happening as x approaches 6 from the left. What do we have? If you said 0, that's correct. And then as we approach 6 from the right, we have f of x approaching 0, or the y values approaching 0. Okay, so 0 on both sides. Okay, let's see if we can get 7. So as x approaches 7, remember, when we're approaching a number, we're getting closer to that number. We're not going to be moving away from 7. We're getting closer to 7. It's like 7 now has the gravity, and now our eyes are going to be drawn towards an x value of 7, right? So we'll approach 7 from the left, and what are the y values doing? Getting closer and closer to 3. That's correct. And then as x approaches 7 from the right side, the y values are approaching 3 again. I don't know if you can hear my hands furiously hitting the arrow button to make the x values move. Okay, so that's example 2. Before we move on, I just wanted to give you a quick glimpse to tie in what we were talking about earlier about infinitesimals and see how they relate to these limit concepts. The infinitesimal, the number that's getting closer and closer to 0 when we're taking limits, is that distance between the number that we're getting close to and the x values that we're looking at, right? Like when we're approaching 7 from the right side, that distance from 7 to our x value is shrinking, getting closer and closer to 0. So, so that's what's happening with these infinitesimals. This concept of the infinitesimal, of something approaching 0, is really key to this idea of limits. And again, towards the end of the semester, we're going to be focusing again on limits and what the more formal definition is. And we'll see that thing that's getting closer and closer to 0. That's going to be called delta later on. All right, but for now, let's move on and talk about not infinitesimals, but infinities. So we can use positive infinity and negative infinity to help describe what's going on with this given function below. And I should mention that this goes with example 3. So here are the limits that we're going to try to find. The limit as x approaches 1 from the left, and the limit as x approaches 1 from the right. Let's start with those two. So we'll head over to a bigger version of our graph, and one that we can play around with. So we're going to be drawn towards 1. That's now going to be the x value we're drawn towards. It has like gravity at 1. So we're going to get closer and closer to 1. What does it look like the y values are doing as x approaches 1 from the left? What does it look like is happening? Yeah, if you said that the y values just seem to be getting bigger and bigger and bigger without bound, or something along those lines, that would be correct. The y values are shooting up to positive infinity, we can say. Now we can't know for sure because the graph cuts off right here, but if we're to take the behavior of this graph and assume that it continues on in this direction, knowing also that there's this dashed line right here, which we call a vertical asymptote, that indicates that the graph is getting closer and closer to that vertical asymptote, and therefore is moving up to positive infinity. So in this case, we would say that the limit as x approaches 1 from the left would be positive infinity. Now we can either write that by saying positive infinity, by writing positive infinity, or as we'll just write infinity. We don't need to put the positive in front of it. And that's what we'll do for the most part. It'll be assumed that if you don't put a positive in front, then it's assumed to be positive. Just like you don't have to write positive 2 every single time you want to write 2. Okay, now it is a little funny to say equals positive infinity or equals infinity, but that's just the notation that's used. It's a way to indicate that the y values are getting bigger and bigger and bigger without bound as the x values are approaching, in this case, 1 from the left. Let's look at approaching 1 from the right. So we'll go over here to the right of 1 and get closer and closer to 1 and see what happens. What are the y values doing in this case? Yeah, they're falling down to negative infinity. Negative 11.5, negative 13.29, negative 15.67. They keep falling down towards negative infinity. So we're going to write that for this limit, as x approaches 1 from the right, f of x is approaching negative infinity. Now, we mentioned that this vertical asymptote was an indicator that this kind of behavior was happening, that the graph is going up to positive infinity or going down to negative infinity. And it works in the opposite direction as well. If you happen to know that the limit as x approaches 1 from the left is equal to positive infinity, well, that's going to tell you that you're going to have a vertical asymptote. We'll talk a little bit more about that later in the packet. Now as x approaches 3 from the left and right, let's take a look. So as x approaches 3 from the left, what are the y values approaching? If you said 1, that would be correct. Let's jot that down. And as x approaches 3 from the right, what are the y values approaching? If you said positive infinity, that would be correct. Remember, your eyes should be drawn towards 3. There's a lot of stuff to distract you here, so I know it's easy to feel distracted by me switching between all these different screens. But not only that, but also the dashed horizontal asymptotes and the vertical asymptotes, another horizontal asymptote. It looks like a crazy game of tic-tac-toe here. But remember, when you're thinking about a limit approaching a number, you're going to be drawn towards that number. You're not going to be traveling down this path of the curve because we're not approaching, because that would be going away from 3. We're going to be going closer and closer to 3. And you could start off far, but eventually you want to see what's happening eventually as you get closer and closer and closer to 3. What's the behavior? There's all kinds of crazy behavior. If you start from an x value that's really far from here, it kind of goes down and then all of a sudden it jumps down to negative infinity. But you want to see what happens as you get closer and closer and closer and closer to what is that end behavior looking like. And it looks like it's getting closer and closer to positive infinity. That's what the y values are approaching. All right, well, let's take a look at 4. So as x approaches 4, now 4 is what we're going to approach. So as x approaches 4 from the left, the y values are falling down to negative infinity. So we're going to write negative infinity. And then as x approaches 4 from the right, what do we have here? If you said 2, that would be correct. That's like one of our examples in example 2. All right, now here's something new. The limit as x approaches infinity. Okay, so now it's not that the y values are going to infinity, it's that now the inputs are going to infinity. The x values are going to infinity. So what is that going to look like on the graph? What do you think, how can you describe x approaching infinity? Well, if you said something like this dot is moving to the right, or your inputs are moving to the right, are getting bigger and bigger and bigger, then that would be correct. That's basically the idea. If x is going to infinity, that means it's going 1, 2, 3, 4, 5, 6, 7, 8. It's going to the right. So what happens to the y values of the graph as your inputs go to the right? What is happening? It looks like the y values are getting closer and closer to a y value of 3, right? This graph has an arrow here that indicates, even if it didn't have an arrow and it just kind of went off the side of the window here, you can see that this horizontal asymptote is what the graph is going to be approaching. So it's getting closer and closer to a y value of 3. The horizontal asymptote in this particular case is kind of like a ceiling, and the graph gets closer and closer to that ceiling but never quite touches it. So here the y values are getting closer and closer to 3 as the x values get closer to infinity, or go towards infinity. You can't really get close to infinity, I guess. It just goes to infinity. What about the limit as x approaches negative infinity? What does that look like visually? Uh-oh, I've lost my input. Oh, there it is. Okay. Well, if you said taking your input to the left, that's what x going to negative infinity means, then that would be correct. That's visually what it looks like, is dragging that x value towards larger negative numbers, so going to the left. And what are the y values doing as your inputs approach negative infinity or go to negative infinity? If you said the y values look like they're approaching 0, that would be correct. And that's helped by seeing this horizontal asymptote at y equals 0. That's the graph. That's the line that the graph is getting closer and closer to. So the y values are getting closer and closer to 0. And actually, if we drag it further and further and further, you can see those inputs, those are the x values. You can see the outputs, those are the y values, getting closer and closer to 0. That's all for this part. Thanks so much for watching, and I'll see you in the next part.